I'm going to go through each of these problems in homework 6, and I may not go through the problem completely, but just kind of give you the gist of how to go about solving it, okay? So the first problem, a researcher collects a simple random sample of grade point averages of statistics students, and she calculates the mean of the sample. Okay. Under what conditions can the sample mean be treated as a value from a population having a normal distribution? Okay, so this goes back to, and I'll just show you this really quick, the handout that we had from Module 6. And it talks about the different conditions that you have to satisfy in order to use the central limit theorem, which is the key thing here, right? The key result. And so if we look at this, and feel free to refer the students back to this, okay? They should use the notes. I mean, this is what they're going to be using on the exam, right? So this tells us that, you know, if the sample is random and large enough, meaning it has at least 30 in the sample, or if it's symmetric and mound shaped, okay? And sometimes the book will use normal as a synonym for symmetric and mound shaped, and either one's fine, okay? So if the population has, notice we're already told it's a random sample, right? So if it has a normal distribution, it gets a pass, regardless of sample size. If they collect more than 30, that's also good. If the sample has more than 80, I'm sorry, actually this is not the number of samples. This is the number of individuals in the sample, right? So more than 30 samples won't help because each of these students themselves is actually one data value, okay? If the population of statistics students comes from a normal distribution, this last one doesn't even make any sense, right? So we go ahead and check. Okay, good. Assume that females have pulse rates that are normally distributed with a mean of 76 beats per minute and the population standard deviation of 12.5 beats per minute, okay? So one of the things the students have to understand is the difference between an individual value, okay, and the value of a variable and the value of the estimator, right? So if one adult female is randomly selected, there we're looking at the variable. What is the pulse? What is the probability her pulse rate's less than 80 beats per minute? So here we're going to go and we're going to use StatCrunch, right? So we go to StatCrunch, normal calculator. Let's open up a whole new table here. Okay. And we just start putting in the values that we're given, right? So we go to StatCrunch, calculator, normal. And we're told that the mean is 76. Standard deviation is 12.5. Okay. And we want to know the probability that a randomly selected person has a pulse rate less than 80. Let's go ahead and put that in. And that's going to be our value. Okay. And they're not asking it for it as a percentage. So we just go ahead and put that in. And so what they're going to be doing here is looking at the difference between an individual and the estimators, right? So if 16 adult females are randomly selected, find the probability they have a pulse rate with a mean less than 80 beats per minute. So now we're looking at X bar, right? So we have to know what sample means look like from this population. And this is what the central limit theorem tells us. Okay? And in fact, we could set up a little Excel table if we wanted to, all right? Where we have sigma x, the standard deviation of our variable, n, and sigma x bar, That's the standard deviation of the sample mean. So our standard deviation of our variable was 12.5, and we had 16 people in our sample, right? So this last one is going to be equal to the standard deviation divided by the square root of the sample size, which is just going to be 4, but we might have a different value from another problem. So now this is the standard deviation for the sample means from sample sizes 16, right? And now I can go ahead and put all this in, all right? I'm going to go back up to StatCrunch, and all I'm going to do is just change this standard deviation now to whatever it is in this Excel file, which is 3.125. And there we are. And you can see that the width of this distribution has decreased because the sample mean, the standard deviation decreases with the sample size, right? So go ahead and copy and paste. All right. So why can the normal distribution be used even though the sample size does not exceed 30? It's because we're told that they're normally distributed, right? So, and these are little, since the original population has a normal distribution, the sample means, okay. The other ones are a little awkwardly worded. Since the distribution of sample means not individuals is of sample means, not individuals, the distribution is a normal distribution for any sample size. That's definitely not true, okay? That's why, in fact, we have to have this condition on the sample size because this statement's not true. Okay. Suppose an airline uses a seat width of 17.1 inches. Okay, so this is this is going to be probably a mean sort of problem, right? Assume men have hip widths that are normally distributed with a mean of 14.8 inches and a standard deviation of 1 inch. And this is actually the same sort of problem as the last one, right? They're talking about the individual versus the estimators, and we're going to have to use the central limit theorem. So that's not so bad. Okay. So let's see. The blank tells us that for a population of any distribution, okay, the distribution of sample means approaches a normal distribution as the sample size increases, and that's the central limit theorem. Okay, it says that the sample size gets larger and larger, the population of sample means approaches a normal distribution. Okay, good. Okay, so this is an important question, okay? So the standard deviation of the sample means, sigma x bar, is equal to the standard deviation of the variable divided by the square root of the sample size. So this is a consequence of the central limit theorem, right? This is what it's saying. Sigma is the standard deviation of x, my variable. Sigma divided by the square root of n is the standard deviation of x bar. Okay, good. As a sample size increases, the standard deviation of the sampling distribution, which is just the population of sample estimates, it decreases. Right? And we know that because we know that this is the standard deviation of the sample means. And as the sample size gets larger, it gets thinner and thinner. Okay. The amount of water in a bottle is approximately normally distributed with a mean of 2.4 and a standard deviation of 0.025. And so we're doing a similar sort of problem, right? We'll go ahead and work through it though. So the probability that an individual bottle, so we're talking about the variable value, right, contains less than 2.38. Well, again, we're going to use StatCrunch for this, okay? So we bring up StatCrunch, and we say that we have a mean of 2.4, right? And in this case, and again, your numbers are going to be probably a little different, right? 0.025 is a standard deviation. And we want to know that it's the probability that it's less than 2.38. And there we go. One thing you can emphasize to the students is this shaded area, okay? Kind of, make them understand that this number right here is the value of this area when the whole curve is 1, okay? And round to 3 decimal places. Also have them watch the rounding. So a lot of them don't read very carefully, right? And they're used to it being 4 decimal places, and then they'll just keep on using that, and they have to be careful, right? Okay, so now we're going to have 4 bottles, right? And we want to know what is the probability the sample mean amount is less than 2.38. So now we're going to bring up the Excel file and recalculate the standard deviation of the sample mean using the central limit theorem, right? So our standard deviation, you can just put yours in here, right? And my sample size is 4. And now my X bar is just 125. Basically, it just gets divided by half, right? That's all. And if I compute that same value, the probability should it decrease or increase? Well, the probability, if you think about it, the curve is going to become thinner, right? So if you look at this, right, you can see that this area is going to decrease because the curve is coming in, right? There's more probability now between 2.38 and 2.4. And again, round it out to 3 decimal places. So this is really similar to the one that we just had before, right? And it's the same thing, right? If you had 25, you would just change this to 25 and redo the calculation over again, right? What is the sampling distribution of the means? Okay, so this is a different problem now. The diameter of a brand of tennis balls is approximately normally distributed, and they give you the population mean and standard deviation, and they tell you that you're taking a random sample of 12 tennis balls, okay? So what is the sampling distribution of the mean? Well, let's see the possibilities. I mean, we know what it is. It's going to be the distribution of the sample means with this population mean and this population standard deviation divided by the square root of 12. But they really want to know what type of distribution, right? So we already know it's going to be normal because we took a random sample and we're told that the diameters are approximately normal, right? So let's read through these carefully. A is wrong. Okay. B could be right. C is wrong. And D is wrong. So it has to be B. So again, random sample, and if the variable has a normal distribution, you're automatically guaranteed that X bar has a normal distribution. You don't have to even worry about it. Okay. What is the probability? Then you have to go through and do this calculation, right? I'm going to enter the mean here, figure out the standard deviation here, and put it into the calculator, right? Okay. And this is really the same sort of thing, right? This is the population mean of the variable. This is the standard deviation of the variable, and you're going to use n as 16 to recalculate the standard deviation of x bar, and then put this mean, this standard deviation, and this value. And you're going to have to change that to greater than because they want at least. Okay, and so this is nothing new, right? This is one that you basically have done. This shouldn't be hard. Okay, so this is asking them for something a little bit different. So, and this one they're going to have trouble with probably, okay? So what you want to emphasize to them, and they don't really understand this well because they don't get enough practice with sketching these things out, okay? So first of all, we want to identify the symmetrical interval that contains 95% of the sample means for a population with a mean equal to 51 and a standard deviation equal to 12 using a sample size of 36. Okay, so let's take this apart. Okay, so first of all, we're talking about sample means, right? So this is what we're interested in. So we have to know, does the central limit theorem apply? And it does. They don't tell you that this is a random sample that it's taken from, but we're going to assume this. The book is sloppy about that. But when they want you to solve a problem, it's obvious, you have to assume random sample. Okay. And the sample size is above 30. So we know a few things, right? We know that the standard deviation of the variable is 12, and our sample size is 36. Okay, so standard deviation is 2. And we know that mu is given. This is the population mean of 51. Now this is what you want to emphasize to them, okay? This is what you're trying to get here. Okay. So here's what's going on, okay? Our mean is 51. Our standard deviation is 2, okay? And this is for x bar, okay? And they want to know what values bracket the middle 95%. Okay, symmetric interval that includes 95% of the sample means. Okay? So we want the values, we don't know where they are, okay? But they're going to be the same distance from the mean, right? And they're going to contain 95% of the population. And since there's 5% in these tails, and these tails are both symmetric, okay? Because we have symmetry here. This is what it means to be a symmetric interval about the mean. This has 2.5% in the tail, right? And this has 2.5% in the tail, which means this is the 97.5th percentile, and this is the 2.5th percentile. So now they have to use StatCrunch, okay? So StatCrunch is going to help them out here. So I'm going to enter everything I know about this problem. The mean is 51, and you enter whatever yours is, right? Standard deviation is 2. And I want to find the value such that there's 2.5% in the left-hand tail of the lower value. So this is my answer here. And then I want there to be 97.5% in the other tail. Okay? And you can test yourself. If you subtract this value from the mean and the lower value from the mean, those should have the same length, right? That's what it means to be a symmetric interval. Okay, good. So they're gonna struggle with that. I know it, but and drawing pictures really helps. You want to give them that intuition pictorially with what the symmetric interval that contains 95% of the values actually means. Okay. Assume the average price for a movie. So this is going to be my mean, right? We know the population standard deviation, the sample size. So the standard error is sigma x bar, okay? So the standard error, and this isn't a term that we use a lot, but we abbreviate it SE. Okay? It's the standard deviation of the sample means, which is equal to the standard deviation of the variable divided by the square root of n. And they're given that information. They can figure that out, right, from the problem. Okay? Let's see. At a certain restaurant in Ohio, the number of minutes that diners spend at a table has a major impact. Yes, it does. Suppose the average number of the diners, okay, is 98 minutes. So they're giving us the population mean, sample standard deviation, and we're told that this variable, minutes spent at the table, also follows a normal distribution. And that's important because now they're asking a question about the average time, okay, that we're going to have for 9 tables. All right. So now you can use the central limit theorem because they don't say it's a random sample, okay, but we have to assume because they want us to obviously give a value. And we know that we can use a sample size of 9 because we're told that the number of minutes follows the normal distribution. So again, this is a straightforward, calculation using the central limit theorem. Okay, I hope that helps. If you have any questions or anything that doesn't seem clear, let me know because chances are that's something that doesn't seem clear to the students either. And I definitely want to make sure that they're not missing anything. All right, thanks.